Alright, so in this session, let's make a compiler for the brainfuck language. Basically, this is like a really simple language. It has only a few symbols that you can use to create programs, but it's nonetheless Turing complete, so you can write anything in it. And it's also a really good example to make interpreters for or any type of like parsing on it. So yeah, this is the language, how it works. It has basically a memory array of bytes, which has 30,000 cells, so that's the memory size that we are going to have. Okay, and the pointer starts at the first cell, of course, obviously, and then we have a few um, commands that move our pointer to the left or to the right, like in a Turing machine, basically. Then we have the plus and the minus, which increment or decrement the value at that position. We also have dot and comma, which are basically used for input and output. A dot will print the current value, and the comma will read the value into the memory cell. And yeah, then we have these two instructions, which are like the weirdest ones so far, because we basically need some conditional jumps to be able to have like a Turing complete language, right? So first is the opening square bracket, which will go to the matching closing one if the current cell is pointing at 0, right? And then we have closing bracket. I mean, it will go past it, not to it. It will go to the next instruction. So if we have like a plus after this, it will go to that plus and execute that. And if we encounter closing bracket, then we go back to the next instruction after the matching opening bracket. So I mean, as you see, it's like extremely simple, but you can also have like a semantic analysis phase in your parser just to check if the parentheses are matching. And yeah, um, having like even simple programs is really hard. So uh, we'll test our program afterwards with something like this. We'll copy paste. I guess this is hello world. To be honest, I don't have a brainfuck compiler right now, so we have to build it and see if this really prints hello world. And actually, this is the one with the correct spacing, so we'll test it. And there are even more cool examples. So we have like a Pong game. So I guess this is like a compiler or something, but I was hoping that there is somehow like yeah, whatever. We'll test some of these examples. Oh, I guess maybe this thing actually generates the code. Interesting. And maybe this thing generates the game or something. Anyway, yeah. And I guess also any other character is a comment, so we can ignore it. So yeah, we ignore everything except these characters. It's pretty nice. So yeah, to be honest, I wanted to try to do it in C. It's I guess I don't know. We can do it in Python or something, but makes more sense to do it in C. To be fair. Okay. So yeah, let's start with the usual print hello world. Okay. Perfect. And yeah, now I was basically thinking that maybe like this CLI tool should get the program as let's say read it from standard input and then write it to standard output. Maybe that's like write the assembly, because yeah, that's what I was thinking to do, like compile it to assembly and then use NASM to to create like the O file and then link it into an executable. So yeah, this is good question, how to read from stdin now, like until end of file. It's see, because to be honest, I'm not really sure how to read from standard in. Yeah, I mean that would be. No, I mean I would like to build a string, so I guess they are using like fgets until a new line, and then like it would be the same way we did the reading from a file for the words when we. I even forgot what that project was, to be honest. Like the dictionary, like the try and autocomplete. Yeah. So maybe we can reuse that thing, but instead of having like a file here, we can use stdin, right? So let me. Complete. I think it was. Yeah, I never. Of course, autocomplete dash C. So yeah, I mean even for this thing, I changed it a bit. I pulled out in autocomplete.h. But yeah, okay. So basically, this is what I was thinking. Like, let's copy this function and let's change it to something like um, read input program. and let's have it return a chart pointer to the program, right? And yeah, we don't really need any arguments. It will be well, actually, I had an idea, like what if it's we give it a name, and if the name is null, then we read from std, right? Okay, so now we need the, oh my god, the a char pointer to the program, and yeah, let's say first this is like null, or we can even malloc, and yeah, let's define some stuff like max len. Let's say it's like this for a single line. Okay, and I mean let's do like 8,000, like this number for the max program length, and let's use calloc just to have everything set to 0. Okay, so here we do this. So if I would rather have this set to null maybe, and now if name equals to null, then f is std, right? And here if name, I could check like this, it's not null, then f close, and then return program. Okay, so now while we, yeah, like if we said max program length, but I would like to realloc in case, you know, so maybe let's call it like program len. And we also need unsigned, yeah, like program length should be like the current program length. And yeah, if we, okay, we need include string. So pretty much if the program length, yeah, no, that's not good. We need like how many bytes we use, right? So if the program length is less than adding these two strings together, we multiply the program length. Well, I mean it works like the append, right? So we need a count unsigned int capacity, which is program length. So if the count is less, then we do capacity times 2, and here we realloc for this size. Okay, then we um, oh my god, I mean this computation is not really correct, so wait, f gets returns doesn't return anything. So here we can have like sign int len is the length of the, I don't know why I cannot type this word. Anyway, so if the capacity is less than count plus len, then we need to realloc. We need to increase the capacity. Okay. Then we string concat the program and the buffer. Okay. We need to increase the count, and I would also set this to 0 just in case. And then just to make sure we don't do anything wrong, we also add 1 here just to take into account that extra 0 which might appear. Okay, so this is how we might read our input. Okay, let's also do one thing here, which is like, let's copy from argparse. Like now we have argparse, the library, so we can argparse implementation. Let's include it, and yeah, I mean, let's also do something else here. Let's check in argparse the example, right? And yeah, because we might need like here pf compiler, whatever, let's leave it like that. And we need this like argument for file, then we need to get it. And yeah, as I said, we don't really need it to be like, it's not a required argument. We can have it or not, and based on that we read from stdin or from the file. Okay, so now let's get the program. Let's printf, see it, and then we free it. Okay, so let's do that. Now if we, I think it's what, control D. Wait a second. Like if I input something and then press, you have to press twice. Okay, whatever. I mean, we can also echo, I guess, something into main. Oh, like this, using, right? Okay, yeah. And how do you specify to echo to not use new line -n? Yeah. Okay, fair enough. So like this works. And if we take this example, and say like hello world.bf, we put that in there, and now let's run. Okay, interesting. Ah, file null. Oh my god. Oh no. I think I know why. Well, I mean, I don't know why, to be honest. Do you really like a description here? I mean, I swear it's so strange because, like, in the testing, I mean, how is it even possible? Like, this thing worked before, right? Like, we even like copy pasted from the example. It's like crazy, dude. Oh my god. Like, let me take the help, put it here. Like, it's so weird. And yeah, where is it? Here. Let's do like this. Okay. And we also need this thing. Like, I'm not sure why it clearly something's not right. I'm not in the right, but I have no idea. Let's remove some stuff because it's oh my god, I'm so dumb. I forgot to put I'm pretty sure someone was yelling this at me, but I forgot to actually parse the arguments. Ah, yeah, okay. So yeah, now now it works. Let's pretend that it didn't happen. Okay, perfect. Now let's so yeah, basically this function is pretty nice. It actually parses, like it reads either from stdin or from the file, depending on whether you provide a name or not. So really nice. Okay, now let's actually like tokenize this bad boy string. So we might need an enum. What the hell? How does it know? Well, I mean, I said here BF compiler, right? So maybe that's why. But yeah, basically, well, I mean, let's keep it in let's keep it in order, right? Let's do move right, move right. I mean, I didn't know you can do that in C. Anyway, increment, decrement, output, input. Um, that's a jump forward and jump backward, right? That's, I guess, the names for them. Cool. Okay, so now let's have um, what do you think? Should we use like dynamic array for? It doesn't really make sense. Oh, actually, yeah, it kind of does because we have also characters that we are gonna ignore. Um, yeah, let's have structure instructions, and yeah, we're gonna have, should it be, I mean, we can have them as characters. 0, 1, 2, 3 is enough, but at the same time the structure is aligned. So if we have a, well, it doesn't even matter, but yeah, like because even the char pointer would be 4 bytes, 4 bytes. No, I like to have this as size t, and this can be an int. Let's make a char pointer, unsigned char pointer, why not? Okay, so for this, yeah, we are gonna need, well, we already have it because it's in argparse.h. So that's really nice. That's really nice. We already have it. Right, da append. Yeah, we have it. Perfect. Then we can just go ahead. Well, let's check argparse.h. I mean, we can have a new function, but yeah, like sure, fair enough. Let's have a new function for, yeah. And what's annoying about the LSP is that if we use this thing with argparse implementation, we need to define it for the LSP specifically. So we need like a file, compiler flags.txt, and we need to define it there to see everything here, because it's really dumb to do it like this. But anyway, so we have instructions new. Let's see. Okay, that works. Let's put this thing here, this thing here, insters, and I mean, I chose the worst name. Okay, and yeah, that this should be called items. Good catch. Okay, perfect. Now let's continue with actually parsing the data. Not before we free it. Not before we free it. Okay. So yeah. Now let's parse the data. So mhm. I think it should be a void. So instructions parse, it should get the structure instructions and the char pointer to the program. Okay, I really don't want to use Copilot for that. I want to do it, and it's nicer to do it yourself. Okay, so let's do a cool thing here. Let's have C. Like I would do it like this because we always put a 0 at the end, so we might as well just take advantage of that. I mean, even string length would need the 0 at the end to work, so it's the same thing basically. Okay, So now we can switch C and yeah, basically, hmm, snippet. Oh, it's not. Anyway, something broke. So we need to add. Well, it's done because we have the append. Okay, and yeah, now I mean we can use Copilot to fill in the rest because it's we already saw one, how to do one, so we might as well just do it. Okay, and if it's the default case, we don't care about that character, we skip it. So now we have all the instructions. Let's parse it. Okay, and now let's interesting. I mean, it prints something. Two, a lot of twos, and then a six. I mean, if increment is the third one, then it's good. Yeah. And one, two, three, four, five. One, two, three, four, five, six. I mean, yeah, seven, because it starts from zero. But no, I saw that you can even have like this, which is like what? I mean, again, yeah, this would print them in using their ASCII codes. So if you want to show them as characters, that would be cool, like this. I mean, let's keep it like this. It's more fun, and it's the same thing. Like it's a character. It's still 1 byte, regardless of how you use it. Anyway, so now we have the tokens. Okay, we have the tokens in our instructions structure. Okay, so yeah, one thing that I don't really like to do now is like the syntactic. No, I think it's semantic analysis. The syntactic one would be with the tokens if we had invalid tokens, but we don't because we ignore all the other tokens. So the next step would be to have some semantic analysis. And you would say, well, but I mean, this language is so simple. How can you even have like something that doesn't make sense in this language, right? Like you just have you just spam this character until you get like the new, I don't know, the new Windows operating system or something. And yeah, that could be right, but we also have these brackets, and they need to be like matching. So it's like the matching parenthesis problem, which kind of sucks in C because we need a stack to solve that. If you know how to solve it, then you know. Yeah, basically, when we like let's take this program as an example. When we encounter a opening bracket, I think we store it on a stack, right? Like we are gonna store this opening bracket on a stack. Then this one also. And then when we encounter closing bracket, we need to check the stack that it has an opening bracket. And if it does, then we remove it. If it doesn't, then it means that we we fucked up basically, and we don't have a opening bracket. And then we have these two that match, and then this one. And if after this one we had another one closing, then it would be GG. So yeah, I mean, making a stack data structure is much easier than the linked list. So basically it looks the same like the linked list, but we only need to add and remove from the start of the list. So I mean, let's try to do it. Why not? Let's continue before main. Let's have a structure stack. Well, I mean, we can do it using our dynamic array, but it wouldn't be as cool, is it? It wouldn't be as cool. I mean, we can make it kind of specific for this problem and be like, okay, the data will be a char, like, well, I mean a char data, and we also have the next pointer, like, just make it like this and not have a void pointer here. That will make it easier. So yeah, let's do it like this. Let's keep it simple. So creating a new, well, this is not correct. Let's make it a node. Let's have a node here next, and structure stack will have the top, and we don't need a count. Okay, so stack new does this basically, and now if we want to free the stack, of course, I mean, let's do free, why not? And yeah, now the classic stack push. So we get the stack like we got the linked list before, and the data, and what we want to do is to push the data into the first cell. So we need to create a new node. We need to create a node. Okay, we want to create a node like this, and we want to set the next of this node to be the first node in our stack, and then we need to say that the top of the stack is n, and then when we do pop stack pop, okay, so well, that's why it makes sense to use void pointer, isn't it? Like, I mean, it doesn't even matter if you do here a void pointer or not. Yeah, I mean, the only issue that I have is that you have to allocate what you put on the stack, but who cares, man? So stack push, let's have void pointer data, and here let's return void pointer. So this makes it easier because here we say null, then we take the first node, we take its data, okay, we move the top of the stack to the next one, and we free the node, and then we return the data. So that works. And there's also maybe stack peak, like looking at the first element. I don't know if we are gonna need stack peak, but who knows. Okay, now let's unsigned int um, yeah, of course we could have had this stack empty function to check if it's empty or not, but yeah, I don't know. Okay, let's make unsigned int matching bracket. Okay, so let's have instructions pointer instructions. I don't know what index is though. Like, why do you need the index? Anyway, well, does it even without the stack? What the hell? Okay, I mean, I'm pretty stupid, I guess, because we only have one kind of bracket, so we can use, instead of using a stack, we can use a counter. Jesus. I mean, that was a bit of a unnecessary, let's call it, precaution. Yep, I mean, sure, fair enough. I guess AI will take over programming in the future. Yeah, because if we have only one kind of bracket, but wait, that means that even if you have multiple kinds of brackets, but it depends if the order of them matters or not. That's why you need a stack. Okay, yeah, whatever. So the conclusion is that I'm pretty dumb. Okay, so okay, what do we want here actually? So we have the depth. So basically, let's go back to the example. If we encounter the opening bracket, we what do we do? We increase this counter. So like we found one opening bracket, then this would be we found two, and this would say okay, decrease the number by one because we found the closing bracket. And then again, if we have the counter set to 0, then if we decrease 1 we get a negative 1, which doesn't work. So let's call this counter, I guess. And if we found a jump forward, we increase the counter by 1. Okay, if we find the jump backward and the counter is 0, then we return false, like 0. Otherwise we decrease the counter, and here we return 1, as in well, if counter is not 0, we return 0, like if you have unmatched opening brackets. Well, wouldn't it be cool to actually have like some sort of error message, right? Like let's think about it. We might want to specify which character. I mean, it would be pretty difficult because we would need to store in these tokens. we might want to store also the location of them in the program, you know. Um, yeah, we might need to store the location and such. That would make it a bit more complicated. But it could be a nice idea to have. But yeah, for now let's leave it like this. And if we have some time at the end, we can change it to, like, instead of having here um, instructions being just characters, we would make a structure called token, which should store the enum thing, and maybe the, like here we should use an index then, and here should be also the index of that character, something like that, maybe even the character itself. Okay, so yeah, that's what we can do. But yeah, this is enough, like matching brackets. If it's not okay, then it's we can shut down the program. So matching. Okay, let's delete the stuff. And here, if not matching bracket, then we say that error. So let's check. Okay, this is fine. But if we add here something like this, unmatched brackets. Okay, good. That's good, I guess. And yeah, now the fun part begins, which is not fun at all, to be honest. I'm just kidding. Uh, Actually generating the assembly. Oof. Okay, yeah, let's search for NASM example first. So I don't really like how it's formatted, but it is what it is. Let's take this example.as. Let's see if it. I think it's like this to specify the architecture or something. -G to have like symbols in case we want to debug, and then the file name, and I guess we don't need -O. I don't know if it even has, well, it has -O. Okay, and then let's use a linker example.o, and let's put the name example, and this should print hello world. Okay, fine. So basically, like, what do we need, like, for the minimal program, let's say? So we need this global start. I don't even know how to. Okay, we don't want to do the right, so we don't need all this part, neither this part. We just need the syscall for exit, right? So this is everything we need for our minimal, like, it just doesn't do anything program. We need the syscall for exit, and that's it. Some section for data. Okay, so let's see. This shouldn't do anything. Okay, perfect. Now the question is, do we even need data? Well, maybe, because as I said, this program has a 30,000 bytes memory array, so we can try to use. Okay, I mean, I have an idea how to do it. We can try to use the break syscall to add 30,000 bytes. Mhm. So let's see, because that thing would be like stealing the minimal program for us. So first, let's do some formatting, because should we have like this? I mean, why not? The comments, okay, fine, whatever. Keep the comments. It's nicer. So, um, let's see. Basically, it's this break syscall, and let's look at what it does. Let's open up one break. So the idea behind break and this break. Now these are the libc version of them. It's not the syscalls, I guess. What? Anyway, doesn't matter. We have break and this break, right? And basically, when you do the syscall, the difference between them, from as far as I understand, is that sbreak actually is like called with a argument set to 0. And if you set argument to 0, then it just returns, or well, I mean, sbreak is actually used to increase the memory size by a number. So if you send a number, it uses that number to increment the segment. And if you send a memory address, it moves like the memory segment to go up until that point. So it includes that point into the memory segment. And yeah, I think pretty much that's the data segment of the program, right? Or is it the BSS? One of one of those. It's basically one of those. I mean, it's the heap, right? It's not the stack. So it increases the memory that the program can use, and this segment goes after your code. So yeah, basically, let's see how we can call it. So we move into rux 12 syscall for break. Okay, let's put. Okay, so yeah, like RDI is the first argument of when you do syscalls and function calls. And let's do this. Let's call um, the syscall for break without any arguments. And as I said, that should give us like the call to this version of it. And when this thing returns, it gives us the starting of that segment. So in this case, it should give us the end of the code section, because yeah, that's the beginning of the data segment. So now let's compile this thing, and let's use GDB. And yeah, I mean, I'm using GDB beta or something. It's like some terminal extension written in Python for GDB. It makes it a bit nicer to work with. I think I saw it first in like hacking stuff, like in Kali Linux. So yeah, that's where it's from. Okay, anyway, let's put a breakpoint into start. That's the entry point. And now let's run it. And I don't know where we are. Can we continue? Interesting. Let's run again because that things looks a bit strange. Anyway, wait. I'm not running the right thing. Should be example. Break start. Run. Okay. So now you can see that here we move into EAX. We move 12, like the syscall for break. Oh, it even shows us the instruction. So we go next. It says no arguments. Okay. We go next again. Now we invoke the syscall, and now in EAX should be, well, in rux should be like the return from the syscall, and it's like 402, and we can see that our program is like around 401. So it kind of makes sense that probably the program ends at 402 or something like the code. I mean, I guess we can go forward a bit, but yeah, I mean, my idea would be that kind of that's where the code section ends and where our data begins. So yeah, now we should keep, like, how can we do it? Because here we need like a variable to hold that value. How can we define a variable in this thing? So like this. So it should be like tape, maybe. Tape. Well, I mean, that's dumb. If you can actually do it like this. Mm-hmm. I mean, it would be nicer to be able to do it like this instead of having to call for a break. Okay, let's see if you can. I don't even know how to search for this thing. Like it's a variable, right? I mean, anyway, let's if we say DQ and this is like a pointer to tape, let's say, right? Like this is how I would do it. And then why does it save pointer to tape? I mean, shouldn't it be like like this. Yeah, and as you see, like this is the, well, I mean, let's run again. So if we go next instruction, next, next, and now we look at rocks, it's like higher up. Anyway. So yeah, I mean, I think what we can do is like move, and now if we print, okay, let's see, gdb print memory px tape like this, or is it mm, no, what would help, like ChatGPT, asking ChatGPT directly. Print a variable from data section. Oh, it's like this symbol. Ooh, yeah, nice. So it's like it was before, or this is like its address, but we want to know its value. What? X examine for hex bytes. Okay, yeah, yeah. No, this is how you do it. You examine the variable. So like the variable is at this location, and this is what it contains, and it's because it's little endian, it's like these two should be swapped around, you know, and these two again should be swapped around to get the value. So basically, yeah, so it works fine. We are able to store that value into the tape. Okay, pretty nice. So we might also need pointer, which will be, well, let's think about it. Python. So it's like 30,000 items. Would this fit into a word? I think so. But yeah, I mean, do we really care about it? Okay, anyway. So now let's let's see how can we allocate 30,000. So assembly example. So this gives us the start, first location. Oh, we can add 5 bytes to the breakpoint. Interesting. Well, I mean, as I said, I thought Well, yeah, makes sense to do it like this probably. I don't remember what Lia does. Lia assembly. Load effective address. Oh, so it's just the address instead of moving it. So like if we, but isn't it like Lia um, we want to move in RDI. Like if we do this, isn't this the same thing as move RDI? Isn't it the same thing? I mean, let's test it. Let's test it. Okay, so we do the syscall again, and this will allocate 30,000 bytes for us. Right. Let's compile, run example. It didn't do anything, so it didn't die basically. That's good news. Let's set the breakpoint to start and run. Okay, so basically I'm curious to see what's gonna be in RDI when we do this. It should be like, I have no idea. So it should have been like rux, which is wait a second. Wait, what the hell am I doing? I just copied that thing. Oh my god. Hmm. Well, this is how it feels to be stupid, I guess. Because yeah, I'm overriding rux with RX with 12, so that's pretty cringe. Like, why wouldn't it work to have tape plus 30,000? Like, I need a reason why this doesn't work, basically. Next instruction, next. Okay, so we save that thing. We move this. And I guess the address looks right to me. Like, let's examine the tape. I have no idea why it's like, why not show it like this? HX hexadecimal. Okay. And like if we just tell it to show us 30,000 in hexadecimal, doesn't work. Anyway, tape plus, would this work? No. Anyway, I'm like thinking, well, 30,000 would be some number in hexadecimal, and if we add it to 403000 whatever, do we get this thing? I think so. I think yeah, I mean, let's try it. Hex 30, they're like 77530, and here we have 7, we have 3530 and 7 on top of 2, so I think yeah, I think it looks all right. So yeah, I think this works. Okay, perfect. So now we allocate this thing, and I guess to free it at the end, you just have to do the same thing, but like move rocks 12, and now point to start and basically free it, right? And our program will be here. Okay, I guess that's like the initial thing, right? Like this frees the allocation. Hopefully. So yeah. Okay, the next step is to print this stuff. So this stuff basically, and then print this stuff at the end. So let's just copy paste everything, and let's have a function that generates assembly. Yeah, whatever, we'll fill in the arguments. So for the arguments we need the instructions. Struct instructions, pointer insters. Yeah, we can use our read function to write to either a file or to std out. So basically let's do something like this. Because it's, why not, right? SharePoint, if we can do it, then why not do it? So we don't need this stuff. This is std out, otherwise it's fopen with write stuff. Okay, and we can use fprintf basically, and here if name is not null we can close it. Okay, so fprintf global start. Well, can we do some vim magic? I don't know. Okay, I don't like that. I want another fprintf just with the backslash n. Okay, and now printf. Yeah, this is annoying. So let's make a macro for this. So gq or like qa. Okay. So 0 insert. Already making a mistake. Okay, let's go again. We go to start. Well, we go to 0, like to the beginning. We press I, F, print F, F, bam. Then we escape, Shift A, backslash N, bam, bam, bam. And I mean, you can also indent it. Escape, press J, Q. Okay, that's what I'm saying. can, I'm not even gonna say it. Okay, yeah, like this is how I would do it. And as I said, this place is where, let's put a to do implement. I mean, obviously. Ah, yeah, this is really sad. So generate assembly, but not to file. We need here another output main. So to output, let's GCC our main, and let's just show that to STT out. Okay, I mean for me it looks really cool though. Like, this is insane. When it will work, it will be so cool, dude. Okay, so yeah, I mean I'm just pausing because it's gonna be a bit hard, I guess. I'm not sure. Let's start with move right and move left. I think these are the easiest ones. So if we go back to our assembly thing, let's have an example for moving the pointer, right? Like, can we ink pointer? Operation size. What, like DQ? Ugh, that sucks. Operation size not specified. Q word or what? Q word. I mean, I have no idea why. The It's so annoying. Why here we have DQ and here you have to say Q word? Like, why not only one thing? Okay, cool. GDB example. Let's break into start, run, and now let's go to ink. I mean, basically it can do. Oh, let's first examine for hexadecimal from the pointer. So it's 0. Nice. Now let's go bam, and now let's examine again. Oh shit, it's 1. Oh my god, that's perfect. Good. So this is how we increment our pointer. Great. Let's copy this bad boy. Let's go into main, and I mean let's have one function for each thingy. So let's have a function generate assembly. What is it? Move right. So I think we just know that it's like we don't care about the instruction, right? We just need file pointer f, file pointer f. And how does it even know that I did this? Oh my god, like this. Oh my god. Here it even does freaking optimizations. Like I was even thinking that maybe that's an idea for some other time to optimize the compiler, but yeah, that's really cool. So I don't really understand why it doesn't want to do it directly. Like you saw that before it was trying to do it keyword directly, but now it wasn't doing it. Okay, so this is how I would do move right. Let's see now move left. So I think it's deck, the right instruction. Hopefully. What else do we need? We need increment and decrement. So let's just create these as increment, decrement. For now it doesn't do anything, but we just create them so that we have output, input, output, input. I mean, for the output, yeah, they were saying that you can have like a buffer where you output and maybe it outputs just at the end or something. Okay, and we have jump forward and jump backward. What the hell? Doing a backflip. Jump forward and jump backward. I mean, I don't even. Okay, okay, yeah. So now instead of this, I mean, let's keep new lines between them. So for size t, let's use size t I equals 0. I is less than instructions. Wait, is it stupid? I don't have this thing. Instructions count I plus plus. And here we need to do a switch basically. And yeah, I mean, we just call the functions. The default doesn't even exist, or maybe, yeah, whatever. So yeah, let's see what happens if we compile this and then we main file hello brainfuck. Well, it did all the increments. That's really nice. Okay, let's see how can we implement now the increment and the decrement. So let's go back to our example as so let's say that we want to get into rocks the pointer, load pointer to current cell. Let's move. Well, that's not really correct because we want to move into rocks the tape plus rocks, right? Like we want to index it. Although its idea was really nice to maybe keep in the pointer like memory address. Okay, so here we don't want to load everything, we want to load a byte. How can we say that? Like this, we load the full pointer because we said DQ. Right, like, I mean, let's go into GDB and see what happens. GDB example. Run, next instruction, next. Okay, so we move this thing into rocks. So now if we examine, can we do like, or for, oh, yeah, okay, I mean, fair enough, I don't care if it's, but it's 0 basically, rocks. So now if we move into rocks, the that thing, we should get, so let's see, we should basically get into rocks like from that address. Well, it doesn't look good. Wait, what's the value inside rocks? 40300. So it's like an address or what? So basically we moved into rocks like this thing, keyword pointer. I'm questioning this. So if we say this is like from memory, right? Like, but the brackets mean to dereference that address. So we got 0 in here. So if we say tape plus 0 and we dereference it, we should get the memory from here plus this. I think that looks good, although it's strange how it's 0. I was expecting it to be like random values, because I thought that when you allocate memory it gives you random values. But maybe we are lucky and the break doesn't do random values, it does just zeros, and that would be really nice. Although yeah, what I don't know is that here I'm like examining, so that looks, because see, like in racks we have an address, we don't have a value. So let's run again. So here when I do this, what do we have in racks? We have 0. Which makes sense because we moved like without any increments. So if we inc the word pointer, what do we get here now? Let's check this example. Let's break start. Let's continue. Let's run. Let's next instruction it until we get to. Okay, so we increment this, and if we examine again for bytes at pointer, we see that it's incremented. Right, that's Nice. If we next instruction it, we see that we moved that pointer inside rocks. So we moved one. Okay. So now let's try to examine for hex, but tape. It gives us 0. Well, you see it's like an address. Oh no, wait a second. Yeah, I forgot, I'm stupid. Tape is actually a pointer, so we need to dereference tape and then add racks and then dereference everything. So we actually want to, yeah, so basically I don't know if this is possible, but we need to do something like this, and if this doesn't work, then we need to do it in 2 steps. Let's see. Yeah, okay, so we need to move rocks and tape like this. We need to take the value from tape, which is the value from tape is the starting point of our array, and after that we need to, well, let's move it in I don't know, rbx, and here we need to do this. Oh my god, yeah, let's not talk about that. Let's imagine that I didn't just do that, because you can't add registers like that. You have to use like operations. Okay, next instruction, next. Here we increment that thing, we load it. Okay, it's loaded, it's 1. Now we load the value from tape, which is this thing, pretty nice. Then we add the thingy, and we get the value, like the address in memory where we want to look at. Okay, and then we load that thing into rocks, which is basically 0. Okay, this is how damn it, how we load. But what's cool about this thing now is that we don't even need to move it, right? We just need to ink 1 byte from rocks. So basically what we do is move into rocks the pointer. Well, I think I can even do this better. So can I add here tape like this? Would this even work? It looks like it works. And what I would like to do is actually do like move and add here. Load the pointer to the tape, add pointer to. So like this looks more like how you do it in C, right? Like you have the pointer to a variable and you add the offset to it, and then you do the operation on the first one. So I think this is how should work. Let's see. Let's run it, and now let's go to that bad boy. So in rocks we should have 403. Okay, then we should now basically go to that thing with the 1 here, and now we should increment the byte, and it's 1 there. really nice. So this is how you do it. Okay, now the problem is, what happens if you, let's say, do too many ads and you overflow? Does it go back to zero? Because that's a good question. Because that's how you do it in Brainfuck. You actually, if you overflow, you go back. And I'm not sure if, I mean, it would make sense that this happens, but let's test it. So let's add, let's add 255 to it. I think that's a good number. And then let's see. So break, start, run, and then next instruction. Okay, whatever. Let's go. Let's do this. So now we should see here 0xff, and if we increment it, what happens? It goes back to 0. Okay, that's good, because um, I saw here in uh, in an example how to implement like booleans, and it was like, it was this. So it was something like, if you have 255 and you use plus, you make it 0, which is false, and if you use minus, you make it back to that value, which makes it true, but I don't find that. Um, yeah, I mean, the, it looks fine, doesn't it? Okay, another idea, just to move it a bit more, like let's do 2 increments here, just to see if that, because it makes sense to work like that, because brainfuck is really simple, so it should make sense to have it like extremely easy for whoever makes the compiler, you know. So let's see this, let's increment twice, let's do all of that, and yeah, now should be still 0. So let's look at this address, let's examine 4 bytes at the address of our buffer, of our tape, and we should see all zeros. That's good. Let's run again and do some next instructions until we get to this point. And now we should see 0xff. Okay, that's good. And if we increment it, it goes back to 0, which is nice. Perfect. Perfect. So yeah, this is how we do. Well, you know, I would like to have also the comment. It would look nice if we also have the comment. Looks better, doesn't it? Okay, let's decrement the pointer. Let's take this. Let's see if I mean, it would probably work like this. That would be ideal. But you know, like, yeah, like instead of having this pointer here, what if we modified the tape pointer? No? What if we modify the tape pointer directly? So like, what if pointer was actually not 0, 1, 2, 3, but what if it was the this thing? Like, what if we do before everything a move into, like, actually here, like a move into pointer, we move rocks and we keep tape just so we can free it afterwards, and we use pointer as the beginning of the tape, like that would work, right? So yeah, I mean, let's see. So we could move here pointer rocks. Okay, so when we increment the pointer is the same thing, it doesn't change anything. But when we do here when we, yeah, basically, I mean, you saw that we had to like do this twice and Nazem didn't like it. So I'm just thinking, would it work then? Like, because what we need to do is the word like this, and when I try to compile it like this, it didn't work. See, so that's not gonna work then. So it's easier to do it like this. I mean, sure, fair enough, we can do that, but we still need to two steps. So let's do it like this, and just to see how we need to do it is we need to move into rocks the pointer. Okay, let's not use comments. And then we need to move like this. Well, can't we just do that? I mean, it's the same thing. Yeah, and if we gdb break main, break start actually, we run it and we go. So yeah, we move this. So in rocks we should have that thing, and if we do this we should have a one. Yeah, so this would work. See, like if we do this thing here and we keep inside of pointer, instead of having a number we have the address directly, so we don't have to do the add here. But I don't know if that's what we want. I mean, sure, fair enough, why not? Let's do it like this. We just need to add this thing here, and let's do it. Oops. So yeah, why not? We can try it. It's like shorter, less assembly basically, I wanted to say. So we have this. We can use our macro. basically this would be move pointer to current cell to rocks and then increment it. Yeah, you can't do like Copilot was trying to use memory dereferencing twice, like that didn't work. Maybe it's like another assembler, but for NASM it didn't work. Okay, so decrement. Now it's interesting, how can we do output? Ugh. And even input. And the even better question is like the jumping forward and backward. For jumping, I think we might need the instruction pointer and the I index where we are at. Because if we jump forward, we just need to find the next closing bracket. It's not that difficult. Wait, am I fucking? No, you just have to. Yeah, we might need a counter for labels. Yeah, we just need a counter for labels. So yeah, okay, let's do the jumping because output and input are kind of meh. So yeah, basically um like we might need some labels here. Because you know the jump is not really difficult. It's basically this one is jump if 0 and this is jump if not 0, but we need some way to label them, and we need some way to label them like in pairs. So yeah, I guess we actually need some other information here, like about which closing bracket is associated with this one, right? Like we might need something like that. So actually building the tokens would make sense for us in the end. Like for at least for building this context of which bracket is connected to which bracket. Yeah, I just have to think about it for a while. Mhm. Another option, I guess, would be, but this is a bit like I'm not sure. Sounds a bit hard to do. Is like when you encounter something like this, you call recursively a function that goes until it finds the matching closing bracket. And it generates this thing, and now it knows that it has to put a label here after this for this one, and maybe before this, or I mean after this one for the closing one. You know, like that's also an option. So like when we find this thing, so this could be like a separate function then. And when we find this, we have to generate a label, then continue with the generation of the assembly normally, like this part. And then when we find the jump backward, we put the same label after it, then return from the function maybe. Yeah, could be like that. Return from the function. Yeah, could be something like that. So we keep everything like this, but we just have to move this for loop into a separate recursive function. Yeah, I mean let's try it. So yeah, I guess Copilot was right all along. Again, generate assembly block. Let's call it block. File pointer F. We give it all the instructions in. Okay, we need the size t start. We don't really need the end. The end is like I would say better to have like pointer to index. So okay, so my idea is we start from index, we just go forward. Okay, we generate the assembly as we did before, like nothing changes here. Okay, but when we find a jump forward, we need to do something. Like, sure, fair enough, we generate the assembly to jump forward. And here let's call index should be 0 and generate assembly block. Okay, and now how should this work? So basically, yeah, we generate the jump forward. Um, jump forward. Hmm. Like when we find the jump forward, we should generate the code and then we should generate the assembly block that's inside. Like generate assembly block. We should pass it the index and then immediately afterwards should we generate the assembly jump backward, and in case we find this, we just return. I think something like that. But here, let's say while index like this, and here let's dereference it. And I guess every time we finish the loop, we increase the index. Okay, this will generate the same. Here we need to generate assembly block before. After we generate the assembly block, we might need to generate assembly jump forward. We might need to do this. Okay, unsigned, and I would have like label equals index, let's say unsigned. Oh, do you need like this shit? Okay, so we get this thing, the label, we generate the jump forward, and I guess for jump forward we need a label, and for jump backward we need a label, right? So here we generate then the assembly block for the instructions in between them. So index will point to this one, but here we need to increment the index, right? Before we generate this thing, we need to increment the index. Okay, so the labels will be the same and pretty much unique because the index will always increase. And I think this is the way to do it. And when we find a jump backward, I mean, we could, yeah, pretty much just, no. I would just return in case we find a jump backward. So we find the jump backward, we stop. This function exits and comes here. Because we already made sure that these brackets are not unmatched. So we already did like matching brackets, the semantic analysis. So yeah, I think this is how I would do it. We generate the jump forward, we go recursively and generate what's inside, and after it finishes, like after it finds the jump backward, it exits and it actually does the jump backward. And here it it goes past the jump backward thing. Okay, I think this should do it. So here we need unsigned int label. Oopsie doopsie. Unsigned int label. So jump forward is, as I said, jump if 0. So we need to move, we basically need to do this to get we need like this. Then we need to compare the byte. Wait, I mean, sure, I would do it like this, but jump equal. Like this is how compare works. Okay, let's see. So let's say that we have to do again this thing. Move. Wait, let me copy the comment because I like it. Okay, so move pointer to the current cell. Compare, but isn't it? No, compare. Okay, fair enough. Compare byte. Compare byte, and yeah, jump jump equal. Okay, yeah. Then this is how you do it, I guess. I mean, let's delete this stuff and have here loop just to see if it jumps or not. Okay, so let's NASM that thing. Let's break start. Let's run it. Let's go. So yeah, basically syscall whatever. Here we move this thing. So in racks we have that pointer to 0, so it compares it. Jump is taken. Bam, we go back. Okay, perfect. So this is how we do it. Okay, so this should be, I wouldn't call it L, I would say L, let's call it LCB, like label closing bracket, and with the label. And actually, let's see, past, back, jump back the matching, like after it. Okay, so now what else we need to have here? Opening bracket. I don't know why it was like LCF. Opening bracket. We put the label here, like after it. So at this label, we want to jump backward. Oh, I get it. It was like forward and backward. Okay, let's call it um, then B for the backward one and F for the forward one. Okay, jump to the end. Wait, jump to label if equal. Jump to closing bracket if equal. Okay, and here it should be the same thing, but jump not equal, and jump to opening bracket. So yeah, pretty much this is the jumping around. Um, let's try it. Okay, so it looks like, wait, why do I have a, like, why though? Who said to put this thing here? Didn't. Maybe I did by mistake or something. Anyway, looks better like this. Okay, so it's wait, we don't have, yeah, we actually have some jumps. See, like here it's jump to this thing, and here is jump to this thing. So this would, if this happens, it would go here and comes back again and again. And if this happens, it jumps past it. Okay, I think yeah, we're pretty much done. We just need this thing to happen. Let's try to minus o hello world dot asm. Let's see it. Okay, let's try to nasm hello world asm. Oh my god. Well, I call this a success. So at line 17 there is a problem. Like the first problem out of a lot. But why though? Impossible combination of address sizes. Like, I don't even get it. Because here we did move rocks pointer increment byte rocks. It's just that it's pretty weird. Well, let's do elf64 minus g and what all that stuff, because we don't know. And then let's link it. Link hello world.o into hello world. I mean, just not get a segmentation fault. That's oof. This is rough. Well, maybe, but I don't, because I'm thinking that maybe if input is missing, maybe it's something happening. But I feel like hello world shouldn't have any input, so it cannot be that. I mean, we have a simpler example, so let's see. Because I'm thinking that, well, like hello world shouldn't have any problems with this thing. Let's see an example. Well, no. Let's have example dot bf and put this here. Oopsie. And let's now use main on example.bf and like let's put it in example.asm. Okay, and now nasm. Let's do this, and if we run example, it's that's good because we can look into it a bit. Let's break at start. Let's run it, and well, I would like to see. There are so many things here, it's so annoying. Okay, so like before we have these things, we increment pointer to current cell. So let's see, we have two increments to pointer, Then we have this thing, we compare that, and if it's 0 we jump here. Okay, let's see what happens. So here it starts, right? Or not, it's a bit lower, I guess. These are the allocations. Okay, so here we increment our pointer twice, so we go to let's examine. So we this shouldn't have done anything, but if we check this one, there's a tape. Wait, let's examine the pointer. See, the pointer increased by 2, so the pointer now points like to the second byte, which is 0. So here it should jump here, right? So next instruction, the jump is taken, so we should go to LB here, right? So what happens next should be decrement the pointer twice, bang, bim, boom, bam, bam. So if we look at pointer, it should be the same as before. Next instruction. Next instruction is to compare the... Wait, what the... Oh, well, I mean, it's like a construction. Okay, so this is also 0, so it should jump. So it jumps here. It goes to the end. It does that, it does that. Wait, what? Why did it segmentation fault when I called it but not in GDB? That's really strange. That's really strange. Okay, here we need one extra space because of that. I didn't like it. Well, oh no. Yeah, whatever, that doesn't matter. No, I was thinking that if there are like multiple digits, then yeah, I don't get it. Example. Why does it segmentation fault? I mean, what if the tape is somehow like 0 when we use GDB and not 0 when we don't use GDB? That would be really annoying. I mean, what's even more annoying is that it works in GDB. So let's run and yeah, like it just goes. Okay, let's add some stuff here. Like let's so it says move space code. So I mean, this is how you do read, but um, I would like to I mean, let's use our compiler. Why not? Like, what the hell am I doing? Right. Let's put here some like 3 pluses, right? Let's use main and then let's use this and then example. So this is what happens, and if we okay, so here we basically example dot asm. Here we increment our thing 3 times. So that means that if we examine the tape, we should see, obviously, but I was thinking that if we, yeah, if we examine its address, can we like do something like this to not type that? No. Or what if we do like this? Anyway, let's take this. Oh, it's 3, right? Yeah, so we have a 3 in the first position. So let's see. So if we go next, this should do the jump because it's 0. But for the next one, because we went back, it should no longer do the jump, right? Jump is not taken. Okay, perfect. So we go in, we move the pointer, we decrement, we increment our pointer, like we go back to the right, we like move that thing, we go back to the left. So now we compare it with 0, it's not 0, so jump should be taken. Move pointer to current cell to rocks. So let's see, let's examine this thing. It should be 2 and 1, yeah. And if we look at pointer, it should be at 0 at the start. So I don't get it why it's the jump is taken, of course. And now if we look again at this thing, now it shouldn't be taken, right? Because it moved everything. So it just exits. That's why it's interesting. Like it works in GDB, but example, the segmentation faults. It's really strange. I mean, let's do another thing. Let's try to remove all this stuff. Let's keep just the thing. It's still segmentation faults. Let's remove I don't know this part. Let's leave it empty, not do anything inside. This works. So let's do just that. That works. Let's increment this segmentation false. Yeah, that's interesting. So let's go back to not using the pointer like this, and let's say that here we move the others of the tape. Move the others of the tape. Let's add. You're stupid. Let's add here the pointer. Let's add here the pointer, and now let's increment like that. Still doesn't work. If we GDB it, just to see that it was like we did it earlier. Run next instruction. So we move this thing. We increment it. Let's examine. So yeah, it's 1, so it works. Okay, I don't get it. What, you want to like move rocks and then increment rocks and then move it. Like if we do this thing, we don't save it at least. Okay, sure, fair enough, we don't care about that. Oh no, just example. Still doesn't work. This is pretty strange though. I mean, the assembly looks fine to be honest, and it works in GDB, so yeah, that's a bit strange. Like everything works up until that. Oh my god, everything works up until actually loading from the tape into memory, so I don't know why. Tape. Because that thing is fine. So like pointer here, and we move it into rocks. Okay, it should be fine. I don't understand. I don't know what the difference between those two. Hmm. Ooh. Pointer. So yeah, to be honest, I have no clue. Should we try with 32? Yeah, I mean it's right. It won't be possible. But yeah, I really don't get that. Plus one. Like it's so stupid. So at the end of this syscall in Rux we should have the beginning address, so we don't even need to move this. We just have the beginning address. So like my idea would be that if I do this, this should work without any problem. Like it doesn't work. I mean, let's see, like segmentation fault when running from outside of GDB. Okay, let's try to use this thing without the randomization. Okay, so let's restart, run. Okay, let's see what we have in Rux. So we have a number, obviously, but what does it signify? Let's look again at man page for break. So here I'm pretty sure it says that if we give it like an address, because that's an address, right? Tape is address, or am I stupid and here should have been like the address of tape. I mean, I don't think it even matters. Like it would be smaller, but it's still an address. So we have this thing there, right? Like, what do we have when we examine this thing? When we examine this thing, I want to say, like, this is the tape. So this weird memory thing is now where our tape starts, right? So like if we now take this thing, so this is where our tape starts. If we examine this thing, it doesn't work, but why? Like it literally says that sends on success returns 0. But here is S break. Okay, what does the break syscall return? mean, here it says that it returns, but that, I mean, that doesn't look like -1 to me, regardless of I mean, what? Yeah, so it here it returns something, but I don't know what that is. Right, like no idea what that is. Rocks was 12 because the syscall. Move abs. So here we move this thing. So what? Oof. So do I really need like this thing? Like when I do, okay, let's run again the compiler and everything. Okay, fair enough, whatever, doesn't matter. Let's see, let's do the set again. Let's break at start, let's run, and let's see what value we have now in rocks. So we have C330000. So that's like the starting point, right? So if we now take a look at this, like we might not be able to examine this thing though, because it's outside of the memory space, right? So if we now, next instruction, so can we print, can we print tape now that it's so tape is 4020, right? And if we try to look at this value, we should see the C3 whatever thing. Yeah. So actually the mistake is that here we don't do tape plus 3000. We, what if we do just this, just 3000? What if we do just that? Set whatever, set randomization, let's break, let's run, let's run next instruction a couple of times. So now in rocks we should have that random stuff. Let's do again. Let's do it like this. Let's see, so let's see what we get in rocks. We get the beginning, and if we now try to examine here something for h from this address, we still cannot access it. But yeah, like my idea would now be, so here we overrode racks. So what if we add racks 3000 and then we move racks into RDI like this. What if we do it like this? Well, I mean, we can put it in a nice order or something, but let's see. So let's next instruction it a couple of times. Okay, let's syscall, and now Rax is pointing at something like 0. So the let's print our tape. Well, that was cool. Let's actually examine the tape. Examine for hex. Okay, so now let's try to examine from this address for hx, and then we need to add this thing at the end. Okay, this works. This works now. So yeah, I mean, I'm not really sure I understand it, but I think that we had somehow to dereference tape, like take its address, not the value when we did the adding. So I mean, it is what it is. Let's copy this thing and put it into main. So we need to replace this part right here. So this part with this, and now let's gcc our main, and let's hello world this bad boy. Okay, let's, god damn it, let's ld hello world dot o minus o hello world, and now if we run it, let's clean a bit the code, because there are too many things, and I think that it's, well, I shouldn't have deleted that. Let's delete this, let's delete this, let's delete this. Let's also delete the example. Now let's compile it. Okay, let's take the example and create this thing. So yeah, now I think, I mean, why wouldn't it work, right? Example, no, nasm. Okay, and now let's link the example. I mean, let's do it like this, why not? Okay, so the example works. Okay, so that was like a problem, I guess. But let's see now for the, let's call it example, why not? I don't really mind. So now let's do this, and now also hello world works, right? So yeah, now it's pretty large. So yeah, that was the problem. The thing is that we didn't dereference the tape when we added 30,000 here, so that's what caused the issue. So yeah, this is pretty much a large part of the compiler, but yeah, I would say that let's try to do the output and the input next time, and maybe also try to do some optimizations, and maybe I'll also try to have a structure here for the tokens. So let's add some to-dos. To do have a struct for tokens, okay, so that we can have error messages in the like here add error messages, add the error messages so that it looks better. And yeah, I mean do this to do this, whatever. I mean, yeah, everyone writes this is a hack, right? Okay, do that. And optimizations, right? Like mm, I mean, let's put it to do think of optimizations. Oh yeah, so I guess that's the plan for next time, to do all the stuff. And yeah, I mean it's like a really cool project, this one. I really want to finish it and see like the hello world. But yeah, we wasted a lot of time with this stupid bug. I mean, it was my fault because I don't really know that much assembly, but to be fair, I really learned quite a lot today, quite a lot of assembly. So yeah, let's see next time and finish this compiler.